Today we are going to be playing with Chapter 6, Section 2, and this is Substitution. So substitution is really just another way to solve systems of equations. So substitution is one of those methods that we can use when either graphing is a problem. Sometimes we might have a y-intercept that is a fraction, or sometimes it's just hard to tell exactly where our solution lies, simply because of the messiness of our graph, or possibly that the numbers get kind of large and they run off of our graph space. So there are other ways, of course, to solve systems of equations, and substitution is one of them. Now, substitution, much like the name says, involves lots and lots of substitution. And so we have three basic steps as we run through this type of problem. Step number one is to make sure that at least one equation has one variable by itself. Now, it doesn't matter which variable is solved for. You could have y equals 3x plus 2, and that would be having a variable by itself. The y is by itself, and it's equal to this 3x plus 2. You could have x equals 2y minus 4, and that would still have one of your variables by itself, and the x would be equal to the 2y minus 4. So it doesn't matter which one. Now, typically, it's y that's by itself, but that doesn't mean that it always has to be that way. Sometimes you will be given equations where y is already by itself. Sometimes you'll be given equations where x is by itself. And sometimes you'll be given equations where neither are by themselves, and you will have to do a little bit of work on your own to make that happen. But for now, we are going to move on to step 2 here. Step 2 involves taking the value that your variable is equal to. So we take that resulting expression and substitute it into the other equation. Okay, so we use the resulting expression. Now, when we talk about the resulting expression, that's a little bit like talking about, not a little bit, it is exactly like talking about this 3x plus 2. That's the resulting expression, or in the second case, the 2y minus 4. So the resulting expression is the other side of the equal sign. So we can use that resulting expression to, I should probably use a pen instead of the highlighter to write here. So we can use the resulting expression to replace the variable in the other equation. So we're going to use the resulting expression to replace the variable in the other equation. Now, once we have done that, once we're in that particular predicament, and we have that ready to go, then we will solve. At this point, you should have only one variable. It might be in two different places, but only one variable. So where before you had both an x and a y, at this point you should now only have x's or only have y's. And that means that we are in a place where we can solve for that variable. So then step 3, the last step then, is to use that resulting answer. So use the resulting solution. Use the resulting solution to replace a variable in either equation. Now, at this point, it doesn't matter which equation you're using. You can use the first equation, the second equation. It doesn't matter which one you choose. So you can use the resulting solution to replace a variable in either equation and then solve. And that gets you both of your answers, both x and y, and your answer is always written in the form x and y as an ordered pair. So I know that when we write down the steps like this, it can be a little bit weird seeing the words, but I think once we get this process rolling, you'll see kind of how this plays out. Now, we will be playing with roughly 4 different types of problems. We'll have problems where both variables, both equations have a variable by itself, equation where one variable is by itself, and then we will have a couple of equations where neither variable is by itself. And we also need to talk about what happens when we have no solution or infinitely many solutions, much like we did yesterday with the graphing. So, all right, here we go. So let's start with example number 1. So in example number 1, we are given the 2 equations, the system of equations y equals 2x plus 1 and 3x plus y is equal to -9. Now, in this particular problem, step 1 is already taken care of. We have one equation where where a variable is by itself, and that equation is the first one, and y is by itself. I like to go in and put parentheses around what y is equal to. Now, what I'm going to do in step 2 then is to go into the second equation, and in that second equation, I'm going to replace y with what y is equal to, those parentheses from before. And so what I have now in my step 2 is I have 3x plus, now instead of writing y, I'm going to write the new phrase here, 2x plus 1, and then I will set it equal to -9, just finishing my equation. Now I realize at this particular point that the parentheses are unnecessary. There is no number in front of my variable or in front of my parentheses, so there's nothing sitting right there, for example, that would make me have to distribute. However, I do really like using the parentheses, because when we wind up getting a variable over here in that particular spot and we do have to distribute it through, it can be really handy to make sure those parentheses are there so that that happens. Right now they're not necessary, but I like to get into the habit of using them. So now it's a matter of starting to simplify. We can combine some like terms. I have x's on the same side of the equal sign. Together they become 5x. Let's go ahead and switch back to red here. Together they become 5x plus 1 equal to -9. And now we can just solve for x like it's a normal equation. And of course we'll start that process by subtracting 1 from both sides, giving me 5x equal to -10. And then dividing by 5 will get me an x value of -2. So currently I have half of my answer. So now the second phase of this, or the third phase I guess I should say, is taking this particular answer and replacing it in either the first equation or the second equation. And it doesn't actually matter which one you choose. You are looking to use this 2 over here to replace either this x here or this x up here in the first equation. I like to use the equation that has the y already by itself, or the variable by itself. I feel like there's less work, but you can plug it into either equation and it will work just fine. So I'm going to use that first equation, and so I will have y equals 2. Now instead of having times x, I will have times -2, as that's the value of x, and then plus 1. So 2 times -2 is -4. -4 plus 1 is, of course, -3, which leaves me with my final solution then as -2 and -3, putting the x value first and the y value second. So that's substitution. We are literally replacing one variable with what that variable is equal to. Now, on occasion, you will come across a problem where both equations have a variable by itself. So in example number 2 here, example number 2, we are dealing with y equal to 3x minus 34 and y equal to 2x minus 5. Now, a lot of people get a little tripped up here, and I can understand why. You're like, well, I don't really know what to put where, but in essence, the same process is about to be used. Y is equal to this 3x minus 34, and I'm going to go into the other equation and replace y with what y is equal to. And so I wind up with a place where I have the 3x minus 34 now equal to the 2x minus 5. And so I took my two equations and I basically set them equal to each other. And so now I just have an equation where variables exist on both sides, and I need to move all my variables to one side and then solve for that variable. I like to bring things to the left when possible, so I'm going to subtract 2x from both sides. Now, again, note that in this particular problem, the parentheses are actually unnecessary. But again, I like to get into the habit of putting these parentheses on here. They will become useful. They definitely will be something that you'll have to be able to use. So don't neglect writing those parentheses. You will regret it if you forget to do that. So here we have a subtraction of 2x on both sides, and that leaves me with x minus 34 equal to negative 5. And so from here we simply solve for x, and we do that by adding 34 to both sides, and that gets me x equal to 29. Now once I have my 29, then I can go in and use this 29 in either the first or the second. It really doesn't matter. I really don't have any desire to multiply by 3, so that I will probably put it into that equation here, the second equation. And so putting that into the second equation, I wind up with y equal to 2, and then times that 29, and then we're going to subtract 5. Now 2 times 29 is 58, and 58 minus 5 is 53, which gives me my final answer then. Let's not move that part of what we're doing. Moving my two answers together, I have my x value of 29, I have my y value of 53, and so I have this ordered pair, which is the solution to those two equations. All right. Now, on occasion, of course, you will have to use those parentheses to do some actual work. So let's see if we can't get a problem where we have to do some work before we even start to solve. And so let's play with example number 3 here. Example number 3. And example number 3 is x plus 2y equal to 6. And then 3x plus, not plus, I apologize, minus 4y equal to 28. Now I want to point out a couple of things here. Because you are so used to solving for y, many of you will still go ahead and try to take, say, the first equation and solve it for y. Now, I am going to go ahead and run that. I want you to see what happens when we solve the first equation for y. If I take x plus 2y equal to 6, and we solve that for y, then I would subtract the x from both sides, and now I have 2y equal to negative x plus 6, and now I have to get the y by itself, and I divide by 2, and we get y equal to negative 1 over 2x plus 3. Now, that equation is just fine for graphing, and there's nothing wrong with having a fraction for a slope. In fact, most slopes are a fraction, but I know that many of you, when you come across a problem like this and there's a fraction involved, I still have many of you that will just quit on me, and I don't want that at all. So rather than dealing with all of that, let's just go ahead and get rid of this, because what I think that you want to make sure that you're doing, let's see if I can even do it that way. Apparently I can't, so I guess we're going to have to erase. So What I think that most of you are going to have to wind up doing when you're working a problem like this is you're going to have to look for the variable that has a specific coefficient. The easiest variable to get by itself will always be the variable that has a coefficient of 1. So when we take a look at our equations here, you'll notice that in the bottom equation, this particular variable x has a coefficient of 3. In the bottom equation, the variable y has a coefficient of -4. In the top equation, the variable y has a coefficient of 2. And here, this variable x in the first equation has a coefficient that is empty, and so it is understood to be a 1. That's the one that we want to play with. So first things first is to take that equation, x plus 2y equal to 6, and we are going to solve it for x. So x plus 2y equal to 6, and I will subtract 2y, and x will be equal to -2y plus 6. Notice that we used the sign of the 6 to write a plus 6 back here. This was subtracting the 2y, so it kept the -2 there. So now we've got that variable by itself, and so we are looking at having x equal to -2y plus 6. And so now we'll go up into that second equation, and we will be taking out the x and replacing it with what x is equal to. I do want to point out, if you ever wind up in this situation and you're replacing y, bear in mind that there is that negative right there, and if you ever have to put something in here for y, and you take this -4, you would have to distribute a negative number through there, so you can't forget the negative there. We're lucky today, however, we're dealing with just the 3 and the x. So here we go, rewriting my equation now. I have, let's get me a little bit recentered here, rewriting my equation, we have 3, and then instead of x, we have -2y plus 6, and then we've got -4y equal to 28. Distributing that 3 through my parentheses gives me -6y plus 18 minus 4y equal to 28. From here I am combining some like terms, and so I have this -6y and this -4y. They are on the same side of the equal sign, so I'm going to combine them together to give me -10y plus 18 equals positive 28. To get y by itself, we will subtract 18 from both sides, and that will wind up leaving me with -10y equal to 10. Dividing by -10 on both sides will give me a y value of -1. Once I have that y value of -1, then I can use that to go up into one of my original equations. Either I can put that -1 in here for this y, I can put it in here for this y, or I can even come down in here and use it here. This is actually where I prefer to use it. I already have x by itself. There's not as much work for me to do. So I'll be putting it into this y. You, again, are welcome to put it into the second equation or the first equation. You should wind up with the same result either way. So x, of course, is going to be equal to -2, and then I'll be replacing the y with a -1. And let's kind of clean that up a little bit here. So again, x is equal to -2 times -1, and then we're adding the 6. And that leaves me with a +2, as a negative times a negative gives me a positive, plus 6, which leaves me with my final answer of 8. Now, together, that x value and that y value give me the ordered pair 8 and -1, which of course I'm going to write in parentheses, because if you don't put it in parentheses, it's not an ordered pair. All right, so I did want to make sure that you've seen several of those types of problems so that you have an idea of how these problems can run. Now, the next thing to play with is, of course, what happens when my variables drop out, as will sometimes happen. So here, as we start example number 4, we've got the problem y equal to 2x minus 4 and negative 6x plus 3y equal to negative 12. Now y is equal to 2x minus 4. This one's ready to go. There was no work for me to do. I'm going to be replacing the y down here in the second equation to get me negative 6x plus 3. And then we will be replacing y with 2x minus 4 and then setting it equal to negative 12. I do need to distribute this 3, leaving me with negative 6x plus 6x minus 12 equal to negative 12. Now, as it turns out, I wind up with some like terms here, and so we can combine the negative 6x and the positive 6x. They are, again, on the exact same side of the equation, which means I'm just going to combine them as written, which means they cancel each other out, leaving me with just negative 12 equal to negative 12. Now, if you remember from our last unit, anytime that our variables drop out and we're left with number and then either equal sign or less than or whatever symbol we have in the middle, it's important to check the veracity or the truthfulness of that statement. So what I'm looking at here is negative 12 equal to negative 12? And of course, that answer is yes, this is indeed a true statement. And because it is a true statement, then what we wind up with is infinitely many solutions. And again, we can't quite use the phrase all real numbers. That implies something a little bit different. We're going to use the phrase infinitely many solutions. I will, of course, take the abbreviation IMS, infinitely many solutions. Now, of course, if you wind up in this particular spot and instead of having a true statement like we do, if you wind up with a false statement, then that is where you would want to run into no solution instead of infinitely many solutions. All right, at this particular point, you have a maze to go pick up, or you should have been it should have been passed out, one or the other. Either it's been passed out to you, or you need to go pick it up. But there is a substitution maze. You've got some problems to work and a maze to follow, and I look forward to seeing all of your work on Monday when we reconvene. And I apologize for being out so many days, and I look forward to working with you again soon. See you guys. Bye.